Math 2414 sequences, video 9, power sequences. So what makes a sequence a power sequence? When the variable is in the exponent only. So we could call these exponential sequences. And the directions for all of these will be the same. Determine whether the following sequences converge. If so, determine the limit. Let's start with A. AN equals 4/5 to the nth power. So the n is in the power and the base is 4/5. Well, we could just start cranking out some values and maybe we can make an observation. Or your intuition might be telling you something. But if we start with the power of 1, we get 4/5. And if we square, we get 16/25. We raise to the third power, we get 64 over 125. We raise to the fourth power, we get, let's see, that'd be 256 over 625. And if we raise to the fifth power, we get 1024 over 3125. And it may not be evident if anything real is going on here, if you're just getting a bunch of numbers. But if we were to turn these into decimals, maybe we can make another observation. For example, 4/5 is a decimal of 0.8. Well, that's easy to square. It would be 64 with 2 decimals. And then if we multiply it by 0.8 again, then we would get 0.512. And if we multiplied by 8/10 again, or 4/5, we would get, let's see, get 0.4096. And then if we did it again, we would get something even larger. Give me 1 second, I'll tell you. 8, carry the 4, 72, 76, carry the 7, 7. 8 times 2 is 32. 0.3276. 0.32768. So what's going on here? Well, they're getting smaller, but how small will they get? Well, we could explore this further, but you would conclude that these are approaching 0. And we can actually get the graphical evidence if we go to Desmos real quick. I have Desmos here. This from old videos. Rid of all this from old videos. And if we were to make the sequence, we'll say n comma 4/5 to the nth power. And we say n equals from 1 to, let's just take it to 20. Working, this should work. Oh, period in the comments, why it didn't work. Okay, so let's put the ordered pair back. N comma 4/5 nth power. And take a look at these dots. See that they are getting progressively smaller and smaller. It looks like they're approaching 0. We can zoom in and see that it's not at 0 yet, but even if we were to continue, why are we not going all the way to 200? Oh, because I'm zoomed in. If we were to continue, we would see that we get progressively closer and closer to 0. Will they ever equal 0? Well, no, because if you think about it, how are we getting from one term to the next? Getting from one term to the next by multiplying by 4/5 over and over again. So it's positive, I'm multiplying by a positive number, so it ought to stay positive. Plus, these are getting smaller and smaller. Now, those two things together don't guarantee that it converges to 0, but I'm telling you right now that this one does. So we'll just summarize and say that this converges to 0. Converges 0. Think of it this way. Multiplying by 4/5 is like multiplying by 0.80. It's like taking 80% of something over and over again. You take 80% of something, it's going to get smaller and smaller. It'll never disappear, but it'll get smaller and smaller and smaller and closer to 0. What about B? Negative 9/5 to the nth power. Well, let's think about this not in terms of cranking out a sequence, but in terms of what's happening to the values every time we multiply by negative 9/5. Well, first off, multiplying by negative is going to cause an alternating signs. So when we put in n equals 1, we get negative 9/5. When we put in n equals 2, maybe I should write these down. When we put in n equals 1, we get negative 9/5. When we put in n equals 2, we get 81/25. When we put in n equals 3, we'll get negative 729/125, and so on and so forth. So these guys are oscillating in terms of signs, they're alternating. And anytime a sequence alternates between signs, if it's going to converge, there's only one way it can do it. It has to converge to 0. Because if it converges to any other number, then the positive and the negative won't be equal. 0 is the only number whose positive and negative are equal to each other. So are these getting smaller and smaller? Well, think about this in terms of decimals. Negative 9/5 is the same as negative 1.8. So if I multiply, forget the negative for a second. If I multiply something by 1.8, it's going to get larger or smaller. Well, since 1.8 is bigger than 1, multiplying by 1.8 will create a larger value. We have two things going on here. Number one, the signs are alternating, and number two, the values are going to get larger and larger and larger. If we were to go into Desmos and look at this, by changing the 4/5 to negative 9/5, back to the home screen for a second. It doesn't take long to see that these points are getting larger and larger as they oscillate. Let me see if I can graph of x equals negative 9/5 x power. It may give me some issues because we're dealing with imaginary numbers. I'm not seeing any graph at all. Are you? If I take off the negative, it's easy. It's going in fact, let's do this. We'll say g of x equals negative f of x. There we go. All right, so, and let's do one more thing. All right, so for the negative values, they're going up to infinity, and for the positive values, they're going up towards infinity. You can see if we zoom out some more. And for the negative values, they're going down to negative infinity. So we're getting oscillating things that are blowing up in opposite directions. Every other term is increasing positively towards positive infinity, and the other terms are decreasing negatively towards negative infinity. So what does that mean in terms of convergence? Well, it means it doesn't. In fact, if we wanted to say anything, we could say that, what could we say? Well, the easiest thing to say is that it diverges. And you don't have to clarify how, but I'm going to be creative and say that it is infinitely oscillatory. Spell that right. I think there's only one S. S. Bottom me. Us, two L's. So in other words, this sequence is blowing up in two directions, positive and negative. Namely, because it's alternating because of the negative, but it's blowing up because the base was too big. This base, small, and why the heck do I have an 8 down there? That's been there the whole time because I just clicked undo. No idea what I was on when I said that. That's just a metaphor or an idiom. I wasn't on anything. But the first one converges to 0. Second one diverges. It's actually infinitely oscillatory. And if, by the way, if we had taken off the negative, then all the numbers would have been positive, and it would just have diverged by infinity. All right, but what about the next one, negative 1 to the nth power? We've talked about this sequence before. As a sequence, it just bounces back and forth. Negative 1 to the first is negative 1, negative 1 to the second is 1, negative 1 to the third is negative 1. So this diverges by oscillation. Maybe that's a better way to say it instead of oscillatory divergence. You can also see that it diverges because it has two subsequences going to different places. Namely, the odd numbered terms converge to negative 1 instantly. The even position terms, I should say, converge to positive 1 instantly. And anytime you have two subsequences diverging to different places, the original sequence is. Anytime you have two subsequences converging to two different limits, then the original sequence must diverge because they can't go to two places. All right. So notice that this base was -1 and this base here was -9/5. As you can tell, we're going to summarize this by focusing on the bases, whether they're positive or negative, and how large or small. Take a look at 3 more, excuse me. That's it. I know they're here. Yeah, they are. All right, these are a little stealthier, except for the last one. But if you look at D, we have dn equals 3 to the n plus 1 over 5 to the n. This doesn't look like a power sequence because the exponent is, the variable is not on one exponent, but notice that its only location is in exponents, and as a consequence, we can do a little bit of algebraic shenanigans to make this something to the nth power. Now, how can we do that? Well, first, let's start by peeling off a 3 from the numerator, writing it as 3 times 3 to the n, which is perfectly allowed because if I were to put the power of 1 back there and put them back together, I would add the exponents to be n plus 1. I'm just taking them back apart. Now, why do I want to do that? So that I can merge the 3 and the 5 together with a single power. Now, you might be saying, but it has a number in front, and you're correct, but the position of the variable in the exponent is what makes this power series. The extra number in front is just sitting there waiting for everything else to happen. Speaking of waiting for stuff to happen, you know what this is going to do as the n approaches infinity? Well, it's kind of the same scenario that we had in the very first one, because if you think of this as a decimal, it's 0.6, which is like 60%. So every time we go from one term to the next, we're multiplying by another 60%, or taking 60% of something. But when you take a 60% of something, it gets smaller. Will it ever disappear to nothing? No, but it'll just keep getting smaller and smaller. So just like the first one, this will get infinitely small. And when I say that, I mean it's approaching 0. So this converges to 0. Go in Desmos and graph it, and you would see correct. What about E, which looks almost like the exact same thing? The only difference is there's a 2 in front of the n on the numerator. And does that change things? Well, it does, but let's massage this so we have a number times something to the nth power, because that's what we're really shooting for here. I guess we could go back here and say that a power sequence is a sequence where the exponent is in the power. That's what I said before. I didn't say there couldn't be other stuff with it. So how would we massage this to have everything to the nth power, or rather one n as one power on one base? Well, the first thing we would do is disconnect the 3 and the 3 to the 2n, just like we did before. But now we have the problem in that the exponent of 3 is an n. It's 2n. But we could rewrite 3 to the 2n as 3 squared to the n by unmultiplying the exponents. And now we have a 3 squared, well, let's call it what it is. 3 squared is 9. And now we can fuse this together as 3 times 9/5 to the n. But wait a minute, we already know this story. This story is kind of connected to the second one here, the -9/5. The negative caused an oscillation, alternating signs, if you will. But the 9/5, because it was as a decimal 1.8, and more importantly, more than 1, that caused it to grow infinitely large. So same thing here. This 9/5 being 1.8 as a decimal. When I multiply by 1.8, things get larger. So the more I multiply, the larger the number it gets. This is going to diverge to infinity. Excuse me. Diverge to infinity. That says diverge, I promise you it does. And let's look at this last one, which is somewhat trivial, but it's here for a reason. The function, which I actually wrote in function notation. Let me go back and rewrite it in subscript notation. Our sequence is f of n equals 1 to the nth power. This sequence is just a bunch of 1s, because 1 to any power is equal to 1. So this is an instant converges to 1. So let's review the different types of things that happened here. Our base was 1, we got convergence to 1. Believe twice, we got convergence to 0. Here and here. And I wish there was one that I had done differently. And 3 times we got divergence. We got divergence here when the base was 9/5. Divergence here when the base was negative 9/5, and divergence here when the base was negative 1. So let's kind of throw on a number line where our bases were and what happened. We had a base of 1, we had a base of negative 1, 0 in the middle. We had a base of 4/5, we had a base of 9/5, which is a little less than 2. And we had a base of negative 9/5, which is back here. And I'm going to put a C and D for converge and diverge. When our base was 4/5, we got convergence to 0. When our base was, we had 4/5 twice, didn't we? Then we had a base of 3/5 also. I left that one out. The 3/5 is about here. And we got convergence to 0. Over here at 9/5, we got divergence to infinity. Back here at negative 9/5, we got divergence by infinite oscillation, but it was still convergent. At negative 1, we got divergence. And at 1, we got convergence. Be careful there, we got convergence to 1. So is there something we can conclude here? Well, in this little chunk between 0 and 1, right here, all the bases are less than 1. So multiplying by them will create a smaller value. So I think it's safe to say that in that interval, we're always going to get convergence. And that includes the number 1, because we got convergence, it was just to the number 1 instead of 0. But what about above? What about over here? When we had a base larger than 1, then multiplying by that number over and over creates a larger value, giving us infinite growth and therefore divergence. Whereas over here, if we multiply by a number less than negative 1, we get the alternating signs, but because the absolute value of that is bigger than 1, multiplying repeatedly makes the absolute value grow. It just oscillates between positive and negative. And so we're getting divergence with an oscillatory nature, one heading towards infinity, one heading towards negative infinity. The only place we really haven't talked about is between negative 1 and 0. But I'll go into you right now, you get convergence there. When you have a base that's between negative 1 and 0, the negative creates the oscillating behavior as expected. But the fact that the absolute value is less than 1 means that you're multiplying by a number that's making the value smaller and smaller and smaller. It's just alternating between positive and negative. But if it's alternating between positive and negative and getting smaller and smaller, then it's approaching 0. So we can say the following. Let's put it in function notation. If f of n, that's not. If a(n) equals r to the n, then say the following. a(n) converges to 0 if negative 1 is less than r is less than 1, which is the same as saying that the absolute value of r is less than 1, because then you're just multiplying by something that's causing the result to get smaller and smaller and smaller. And if it happens to be a negative something, then it's oscillating between being positive and negative while it's getting smaller and it's still converging to 0. a(n) converges to 1 if r is 1. a(n) approaches infinity if r is bigger than 1, so it diverges. And a(n) diverges I want to say it oscillatory. Say it back here. Said something. Said infinitely oscillatory. So it diverges by infinite oscillation. Let's say. The infinite is good enough, but I like to say that it's also oscillating. If r is less than negative 1. And this is going to be important down the road to know when a power sequence will converge. In a nutshell, it converges to 0 if you're between negative 1 and 1. The only other exception is when you are 1, in which case you converge instantly to 1. Remember, instant convergence to 1 when the base is 1. All right, so keep that in mind. If you have a power sequence and your base is small, between negative 1 and 1, convergence to 0. If your base is 1, instant convergence to 1, otherwise diverge. And you really don't have to worry about saying infinite divergence or divergence by infinite.